Hello and welcome back. So, in the last class we were looking at the phase matching conditions and we found the related index matching condition. So, the index matching condition for SHG was like this. So, specifically we can also remove this into N1, N3. So, essentially this means that the refractive index of the harmonic wave and the fundamental light should be same in order to have phase matching. Okay. So, this was my index matching, right. Condition for SHG. Now, in general you can understand that this is not possible, right, normally, because suppose I have an incident wave of frequency 1064 nanometer, then the double the frequency will have an wavelength of 532 nanometer. So, there is a wide gap in the frequency. So, there is something called dispersion, right. So, which is strongly wavelength dependent property. So, in that case the refractive index of say 1064 nanometer and that of 532 nanometer, they are not going to be same. So, if you want to have SHG, you need to have this constraint fulfilled and you know that this is difficult. So, there must be some way out. So, the way out is to use a birefringent crystal. Okay. So, you need nonlinear optic crystals, particularly which will be birefringent, meaning that they will have two different refractive indices. Okay. So, this birefringent crystals, they will have two refractive indexes as they are described as NO and NE. This NO stands for ordinary and this stands for extraordinary. Okay. So, this extraordinary light will pass the fundamental light, ordinary refractive index will take care of the fundamental wave, while the other refractive index, the extraordinary refractive index will take care of the harmonic wave. So, actually what you have to do, you have to first identify the optical axis through which the light will pass through without any kind of change. Okay. So, you have to identify the optic axis of the crystal, that birefringent crystal or the NLO crystal that we are talking about, and you have to send the incident field at a particular angle with respect to that optic axis of the crystal, and this particular angle is dependent on the material that we are using. Okay. So, in that case you can ultimately achieve this condition and you can have SHG process with lot of power, a lot of intensity. Now, we will look into one particular or we will look at the ways to enhance the second harmonic intensity. So, I will just write down one expression for second harmonic intensity. So, second harmonic intensity, which we denote as I2 omega, okay, and this is given by, I will just give you the expression, and one does not have to remember this one. This is second order susceptibility, the effective susceptibility. Multiplied by the square of the path length of the fundamental light through the crystal, multiplied by the square of the incident photon, that is we write as I omega and square. So, this is the expression for the second harmonic intensity through a nonlinear optic crystal. And from here, what are the conditions that we can find out that will help maximizing the second harmonic generation? So, what are they? So, first you can think about this quantity. So, second harmonic intensity depends on the square of the incident power. So, you can imagine that if I increase this power, I can increase the SHG intensity. So, first place, so conditions for achieving large SHG from this formula. So, 1 is increase incident power. Now, that is very obvious from this equation, but there are something to note. I cannot continue increasing the fundamental laser power. Why? Because this laser power beam is intense, and if I increase the intensity of this laser beam too much, it can actually damage the material. Okay. So, this increase will certainly increase the SH power, but up to a certain limit. So, this is limited. I cannot go on increasing the incident power infinitely. So, limited by so called damage threshold of the crystal. So, below the damage threshold is that optimum power beyond which the crystal will get damaged or the material will get damaged. So, I have to be always below that power. So, below that up to this damage threshold, I can keep on increasing the incident power and can get high SH power. Okay. So, the second thing that we can think of the quantity is this one. For a given particular material, this is fixed. Now, if I am searching for some material which will give me very high second harmonic generation, then one condition is that it should have very high second order susceptibility. If I go for macroscopic scale, if I am looking microscopically, then it should have very high value for the second order polarizability. Okay. So, we need material with large second order susceptibility. So, this need actually has opened up a huge field of research where a lot of chemists are actively and physicists are actively involved in preparing material, designing and preparing material that may and that will have large second order susceptibility. Okay. And next is, we must, that material must fulfill the condition for phase matching, delta K equal to 0. Okay. And what is my fourth variable that I can play with is this quantity, that is L, which is the path length through the crystal. So, if I have L larger, obviously I2 omega also will be larger. So, a longer crystal will increase the second harmonic generation more and more. So, these are pretty much the ways to enhance the second harmonic generation capabilities. Okay. Now, we will consider a few practical issues about second harmonic generation. Ready? SHG. So, what is this particular important thing that we should know? It is that for centrosymmetric molecule or material, SHG 0 under electric dipole approximation. So, all this formalism that we are looking at, they are under electric dipole approximation. So, if we do not say specifically everything is under electric dipole approximation, but you should know that there are formalism based on electric quadruple or electric octuple or magnetic dipole are possible. Here we are not going to discuss about that. So, under electric dipole approximation, HHG is 0 for centrosymmetric molecular materials. So, for those who do not know what is a centrosymmetric molecule or material, let me just state that quite briefly. So, let us take a molecule. Okay. So, this is benzene and say this is a phenol. Okay. So, this out of these two molecules, this molecule is known as centrosymmetric molecule, while this is non-centrosymmetric. Why? Because for this molecular structure, there is a symmetry element known as center of inversion or I, such that if I start from any part of the molecule, pass through that particular point and go an equal amount, I will find exactly identical point like from where we have started. So, suppose I start from this particular region and I pass through this one, I reach an equivalent point. Okay. So, the use of the word identical is not completely correct. I must say this is an equivalent point. Okay. So, that is true for any point that we start with, okay, and pass through this one, I reach an equivalent point. This is true for this particular point also. So, if I pass through this end point, I get another similar kind of point or equivalent point. So, that is why whenever any molecule or material, if I take for example a sphere, okay, so if I take a sphere, so does not matter from where I start, if I pass through its center and walk equal amount, I will reach an equivalent point. Okay. So, this kind of molecule or material which has the center of inversion is known as centrosymmetric molecule. For material which does not have a center of inversion, it is non-centrosymmetric. For example, this molecule. Okay. So, this molecule, if I start from here where there is a hydrogen, I will not reach the another equivalent hydrogen here. Instead, I will see an OH group. Okay. So, this is not a centrosymmetric molecule. So, now what is so special about centrosymmetric molecule that we do not observe second harmonic generation from that? So, you can easily find that if you look at the polarization. So, in general, so polarization is given by chi ij. Okay. So, for a moment, if I for simplicity remove this subscript, then I can write it this is written quite in a much simpler form. Okay. So, now consider a centrosymmetric molecule. For a centrosymmetric molecule, if I look from any side, it should be identical. Okay, very similar to the condition where we look at it from a different angle or different position. So, now if I come with an electric field and part of the electronic distribution, so it will get polarized. Okay. So, for a centrosymmetric molecule, if I look at the potential energy due to this electronic disturbance created by a laser field, will be the same irrespective of which way the electric field is acting on. So, for example, if I say I am considering a particular direction, say x, so I can come either from plus x direction or negative x direction. So, for that say I look at the potential energy for this one. So, how we can write it? So, it will be like half chi ij okay, and so on, okay, with a negative sign on this one. Now, if I come with an electric field from plus x direction, what will happen? Say all these are positive. Okay. So, if I consider V plus, that will be equal to this V. Now, if I have my electric field coming from opposite direction, that is my minus E. So, all this E square or E4, E8, these terms will be unaltered, while this E is having odd power will become negative. So, in that case my V minus is not equal to V, right. This is easy to understand. So, if I write explicitly, so V plus is exactly this and my V minus will be minus half chi E square then minus 1/3 chi E cube and again plus again minus other quantities and it will keep going. So, this is definitely not equal to V plus. So, therefore, I will get two different values of the potential energy when I use whether E or minus E. Now, it is we are considering a centrosymmetric molecule. So, it does not matter what is the direction of polarization, the potential energy is also should be very symmetric, it should be an even function. But if I look at the expression of potential energy here, I see that that is not the case. So, this totally in contradiction. The contradiction will be removed if and only if this quantity is equated to 0. That means chi ijk, which is associated with the second order process, if it is 0, then in the potential energy term all the odd power of electric field will be vanished. Let me correct it slightly. I talked about only for second order process. It is valid for any even order process. So, if I consider the next even order process, that is E4 or E6, so those susceptibilities connected to those even order E terms should vanish for centrosymmetric molecule in order to avoid the violation of this case. Okay. So, this is the reason we take chi 2 equals to 0 for centrosymmetric molecule, and this is true for all even order nonlinear process. So, if you consider a non-centrosymmetric molecule on the other hand, so what will be the case? There of course, there is no burden on the potential energy to be identical for different electric fields. Okay. So, if I take plus E or minus E, it is not necessary that the potential energy will be different, because if when the electron oscillates in one direction in case of a non-centrosymmetric molecule, this oscillation does not have to be identical for a non-centrosymmetric molecule when we come with two different electric field, okay, E and minus E. So, that is why in general for centrosymmetric molecule second harmonic generation is 0, because the chi 2 is 0. Okay. Let us quickly have a look at the capabilities of this second order nonlinear optical processes to generate various different wavelengths. So, suppose I start with 1064 nanometer, okay, and if I send this light through a crystal which is a nonlinear optical crystal, then what it will do? It will give 532 nanometer due to SHG. Okay. Now, if I send this 532 nanometer through a dye solution, so say for example, I take rhodamine 6G, then what will happen? It will generate several possible laser wavelengths, because dye laser can, it gives a large emission band, and thereby you can, tune the laser wavelength, selecting a particular wavelength within that emission bandwidth. So, this can give rise to a wavelength range. I will give you say 548 nanometer to 580 nanometer. This is a typical wavelength range that you can get from rhodamine 6G based dye laser when this is pumped with 532 nanometer light, which again is generated from the SHG. Okay. And any wavelength from this range, if it is again passed through a nonlinear optical crystal, then it will give you another range, say 274 to 290 nanometer. Okay. So, you can see that, various wavelengths you can generate. Now, this is not everything. So, if I suppose have another crystal here again, and if I send this light, and if I also send this light, they will mix there within the nonlinear medium, and then I will get another output, and you should be able to guess what output it will give. Okay. In the last class we mentioned about this one, and this should give you approximately 355 nanometer, right. Now, if I put another crystal here and I mix this 1064 nanometer and wavelengths from this range, I can select any one wavelength from this range and I can mix it here. Of course, I can get several different wavelengths depending on which one I am choosing out of this range, and I can get in that way a range of wavelengths, laser wavelengths, which is 362 nanometer to 375 nanometer. All right. And if I take another crystal here and if I allow the mixing of 1064 nanometer and this here, then again I can generate a huge range which is 218 to 228 nanometer, and that is, you can see it is in ultraviolet region. Okay. And if I combine 532 nanometer and these dye outputs, so in an nonlinear optic crystal, I can again get a range of 270 to 277 nanometer again in the UV. I take another crystal and if I mix 532 and 532 nanometer and this output 274 to 290 nanometer, then I can actually generate a very unique set of wavelengths. This is below 200 nanometer and it falls in the vacuum ultraviolet region, which is really otherwise difficult to get, and one needs to take proper care of this particular wavelengths because it is absorbed by pretty much everything. Okay. So also we can combine these two dye outputs in a nonlinear optical crystal, and I can get another set of wavelength in the vacuum ultraviolet like this. So you can see in this whole chart that utilizing the second harmonic process or other some frequency generation process, I can create so many different wavelengths. Okay. And by selecting proper nonlinear optical crystal or other medium, I can get a highly efficient second harmonic generation or some frequency generation. So by which I can create coherent lights of quite narrow band and with high power. Okay. So these are few important things that you should look at, and also you should be able to appreciate this table by choosing a particular wavelength and finding its partner, combining them, and then calculating what will be the resultant frequency. So if you can take any laser, so I have used 1064 nanometer, which is the fundamental wavelength of ND Young laser in the infrared. You can take any other laser, say for example Ti sapphire laser, you can take for the matter ND YVO4, and select the wavelength, and you will be seeing that how you can use nonlinear optics and you can generate various different others other type of wavelengths. Okay. And I was saying that okay, this is not the only advantage of this nonlinear optics, that you can make different wavelengths, but you can use it in various other processes. So there are vast application of nonlinear optics, and second order nonlinear optics is simplest, yes, the most useful. One of the immediate application I can tell you, it is used to probe the pulse width of a very short or ultra short pulse laser. Okay. So now what I am going to talk about is one application of this nonlinear optical process, particularly the second harmonic generation. So this nonlinear optics, of course, gives you the ability to generate various different frequencies having the properties of a laser light, that is coherent, narrow band, high peak power, everything. Okay, high average power. So that is one of the finest application, of course, of lasers in nonlinear optics. Apart from that, there are so many other applications of the nonlinear optical properties which is driven by laser. So I will cite you one example of that one. So we discussed about Ti sapphire laser, which is a laser having ultra short pulse duration. Now, how short those pulses may be? They are in the order of 10 power minus 15 second. So it may be like 10 femtosecond, it may be 50 femtosecond, 100 femtosecond. Now these numbers are really small, and if you have a little bit of knowledge about electronics, you would know that it is not possible for any electronic device to record information in that short period. If you consider say a nanosecond pulse, okay, which is 10 power minus 9 second pulse duration, electronic you can measure it, but not a femtosecond pulse. So there we need to think little differently in order to measure them. So how it is done? This is done by using something called autocorrelation. So, what does autocorrelation mean? I will try to be quite brief in this part. You have a definite pulse duration for a single pulse. Okay. So, let me use two different colors so that it is quite visible. So, a laser will have this pulse duration, and suppose I am saying that this is something like a 50 femtosecond pulse. Okay. And from the same laser I can have another pulse also. Okay. So, which should be identical to the first pulse. Now, if we can allow two pulses from the same laser to interact with each other, I may get some information about the pulse duration. How? That is what I am going to show you. So, now we have learnt about the process SHG, where two photons of same frequency interacts with each other within a nonlinear medium and generate a new third frequency having double the frequency or half of the wavelength. That is my second harmonic generation process. So, if I can put two pulses from the same laser on two different arms somehow and allow them to interact in a nonlinear medium as a function of their time delay. Okay. So, the matter will be clear if I can give a schematic. So, the schematic is as follows. So, suppose I have a laser light coming in this direction. Now, if I put an optics which is known as beam splitter, meaning it will split the beam into 50-50 percentage. How? This side it will reflect in this direction and 50% will transmit in this direction. All right. So, what I have created two beams out of a single beam having 50% of intensity. Now, if I put one mirror here, I call it M1, and then I put a second mirror here, let me call it M2. Out of these two mirrors, if my M2 is movable, meaning it can be translated back and forth. So, now these two light which are split here, they will go hit the mirror and again come back and meet here. Okay. So, this light after meeting here, it will go in this direction, and this light of course it will transmit through this and go in this direction. All right. So, this double headed arrow indicates that light goes and comes back. So, this geometry is known as interferometer, Michelson interferometer. Okay, many of you already know about this one. So, this will lead to interference, okay, constructive or destructive depending on the relative distance between the two beams which are meeting here in time, that is the amount of path that the each arm is having. Depending on that, there will be a phase lag between those two beams, and I will have the corresponding interference. Now, if I put if I focus the beam using a lens, so this is my beam splitter here and this is my lens here, and then I put a nonlinear crystal, envelope crystal, and then I put particular filter which will take only the second harmonic light. So this is filter, and then ultimately it will go to some detector. So in this case, what will happen? This two light will go and it will be focused into the nonlinear crystal, and then you will generate the second harmonic light. Fundamental light is also there. Fundamental light will be filtered here, and only the second harmonic light will come here. All right. So now, for second harmonic generation, so this I showed, this is a pulse width, right? So that means in this axis I have intensity, the number of photons. So second harmonic generation or any other nonlinear process takes place when these two or more photons, they are mixed in within a nonlinear medium. So the efficiency of the process will depend on how many photons are taking part there. Now let us look at this process very clearly. So to start with, I have one pulse going to the detector. Okay. Now I have moved this mirror such that the second pulse is totally outside this envelope. Okay. That means two pulses are not interacting. So there is no mixing between this and this pulse if the situation is like this. Fine. Now if I move this mirror toward this one, so in the next step this will now come here, right. If I move it farther, it will go like this. If I go even farther, at some point of time they will overlap, and then we move farther, it moves out, and then totally it go out. So when these two pulses are quite apart, there is no SHG due to the mixing of those two pulses. There may be background SHG. The moment it starts overlapping with this white one, so let me differentiate this one. Earlier we are using this yellow. So this is pretty much overlapped. So when this green pulse is totally overlapped, then there will be maximum SHG, and when it will pass this pulse, there will be very little SHG. So if I follow the SHG intensity as a function of time which is coming from this delay that this mirror movement can give us, then what I will see? I will see the intensity pattern like this. So essentially this green pulse will map the overall trace of the yellow pulse, correct, because as it goes from this tail to the other tail, it is producing SHG, and for each part I am getting the SHG intensity, maximum being when they are overlapped. So in that way I get my time width of the pulse. So, from the autocorrelation pulse width, one can actually go and find out what is the exact pulse width of the laser, knowing the the particular shape of the pulse. So, what was really difficult to achieve using an electronic device using second harmonic generation technique and allowing the autocorrelation of two pulses by creating a geometry like a Michelson interferometer, one can trace the pulse width of a very short pulse or ultra short pulse laser. Okay. So, there, as I said, there are many other such techniques, such applications of this nonlinear optical processes are there. So, we may not be able to discuss about all those things in the short span of light, but whatever we have shown here, they are quite basic yet extremely important application of process like SHG. Thank you for your attention.